Hi, everyone, and welcome to our first episode of SCN8A Unraveled. I'm Sarah Tay with the International SCN8A Alliance, and today I'll be interviewing Sophie Hill from the University of Michigan in the lab of Dr. Miriam Meisler. Sophie, would you like to introduce yourself?
Hi, everyone. My name's Sophie Hill, and I am a fourth-year PhD student in Miriam Meisler's lab at the University of Michigan.
Well, I am so glad you're here to talk us through some of the exciting work you've done with ASOs. Before we dig into the meat of your research, can you share any basic background information that would be helpful for us to know?
Yes. So in order to understand this paper, you need to know a bit about the central dogma of biology. So starting down here at the bottom, proteins are the things that do the actual work of a cell. So for example, the sodium channel NAV1.6 is a protein. But the information for making proteins is in the DNA. And when a genetic mutation occurs, it alters the DNA. For example, you could have a mutation in the SCN8A gene. There's a step in between DNA and protein called mRNA, or a transcript. And when a person has a mutation in the DNA, it's transmitted through the mRNA and causes the cell to produce the wrong protein. So in the case of NAV1.6, a typically functioning protein is localized within the cell membrane, which is the barrier of the cell. And its job is to allow sodium ions, shown here in red, to pass through the membrane and into the cell. But if you have a mutation in your SCN8A gene that causes the production of an incorrect NAV1.6 protein, you can have problems because the channel is mutated to allow sodium ions to pass through at the wrong time. So in this case, all the sodium ions have been allowed into the cell, and that causes hyperexcitability, which is when neurons fire too frequently. This can cause seizures and result in developmental delays and other symptoms of DEE.
Oh, I see. That makes sense. So now that we've had that nice introduction, what is an ASO and how would it help these problems with the sodium channel?
So what we wanted to do was to ask whether we could reduce the abundance of mutant NAV1.6 proteins. So the idea is that instead of addressing the problem with the sodium channels that causes them to allow too many ions through, we just reduce the overall number of sodium channels and ask whether that compensates. So to do that, one way of reducing protein abundance is to use ASOs to reduce the number of mRNAs. So ASOs, or antisense oligonucleotides, are made up of short stretches of DNA or RNA, and they can work through many different mechanisms. At the moment, there are two ASOs, for example, that are being used or tested in genetic disorders. For example, for spinal muscular atrophy, there's an FDA-approved ASO called Spinraza. And there's also an ASO currently in clinical trials for Dravet syndrome, which is another DEE. So we worked with Ionis Pharmaceuticals to design an ASO that will reduce the abundance of SCN8A mRNA. So in this image, the mRNA is the longer line on top. So the ASO works by binding the SCN8A mRNA. The ASO is that short line on the bottom. And it basically tells another protein to come and break down the SCN8A mRNA. So that reduces the amount of NAV1.6 protein, and hopefully it will make up for the excessive sodium flow that's caused by the mutation.
That is very cool. So how did you test to see if the ASOs did what you predicted?
So we first tested the ASO in unaffected mice, just to make sure that it really does reduce SCN8A mRNA levels. So to test that, we injected the ASO directly into the brain of baby mice that were 2 days old. And 3 weeks later, we harvested the brain and spinal cord of those mice and looked at the amount of SCN8A mRNA. So mice that received the control ASO, which are shown in black dots here and here, had normal levels of SCN8A mRNA in the brain on the left and in the spinal cord on the right. The control ASO is sort of like a placebo. It doesn't affect SCN8A expression. Mice that received the SCN8A ASO, which are shown in open dots here and here, had reduced SCN8A mRNA levels, about 50% of the control mouse expression. So the ASO did what we wanted. And once we observed that it actually worked, we wanted to test the ASO in a mouse that has a genetic mutation of SCN8A. So we engineered these mice to carry the R1872W mutation, which was originally discovered in patients with DEE. And this graph here shows the survival of a group of mice as a function of their age. On the x-axis here is the age of the mouse in days, and on the y-axis is the proportion of mice that are still alive. So the black line up top represents mice with the unmutated SCN8A gene, and they have normal lifespans, so none of them die before 42 days of age. The blue line represents mice with the mutant SCN8A gene, and all of these mice die around 2 weeks of age due to a single lethal seizure. For comparison, a normal mouse lives 2 to 3 years. So this mutation appears to be much more severe in the mouse than in humans. And because these mice die after their first seizure, we were unable to test how well the ASO prevents seizures. So we instead measured how long the mice lived to determine whether the ASO was effective. So we took those same mutant mice and injected ASO into the baby mouse, again, when they were 2 days old. This first line here shows mice that received a control ASO. Their survival is largely the same as untreated mice with the SCN8A mutation. Most of them died around 2 weeks of age. The second line in blue shows mice that received our smallest dose of ASO, which was 15 micrograms. And these mice lived about twice as long as the control-treated mice. The third line here shows mice that received a middle dose of 30 micrograms, and these mice live about 6 weeks. The fourth line shows mice that received our largest single dose of ASO, which was 45 micrograms. And these mice lived about 7 weeks, which is a 3.5-fold improvement in survival. And the final line here shows mice that received 2 doses of ASO. These mice lived the longest of any group we tested, with an average survival around 9 weeks. We hope this means that we could keep giving doses and keep extending the lifespan. Although we were unable to test the effect of the ASO on seizures, we also hope that the ASO would reduce seizure severity or frequency.
That is so fascinating. As promising as this all sounds, are there any potential side effects to this treatment?
Yes, there are. The problem is that SCN8A is a gene you can't live without, which means we can't completely get rid of its mRNA. We have to titrate the level of its expression. So there's always a risk that the dose could be too high, and we anticipate that that would cause movement problems in people.
I see. So while this treatment looks promising, there could also be some serious complications. So then what are the next steps for this ASO to become a treatment available to the public?
So our work right now is preclinical. The next step is to find a pharmaceutical partner who's willing to produce and market the ASO, and then they would prepare it for FDA approval and eventually a clinical trial. So the timescale for that is years. In the lab, we're still working with the ASO. I am currently testing the ASO in other types of mouse epilepsy, and also trying to treat mice with a different mutation with the ASO after they start having seizures to hopefully assess the effect of the ASO on the seizures themselves.
So it will be a while until this is available for families, as we would expect for any new treatment. But this all looks so promising as a means of actually getting at the root of the problem for gain-of-function SCN8A mutations. So thank you so much for your time, Sophie. This was very informative, and I look forward to seeing how this treatment progresses. To the rest of you, thank you for joining us for SCN8A Unraveled, where we unravel the science of SCN8A for you. As always, we look to you to choose what we cover next. So let us know what your biggest SCN8A related questions are in the link below.